Welcome to this session for Universiti Utara, Malaysia computer science students. I am Dr. Alaa Jabbar Almaliki from the School of Computing, and today we are looking at Section 1.6, Areas of Study in Artificial Intelligence. Artificial intelligence is a multidisciplinary field of specialized research, serving as a collection of distinct tools. By the end of this module, you will identify the major AI areas, explain their purpose, recognize real-world applications, and understand how they integrate to build intelligent systems. To give you a roadmap, we can break artificial intelligence down into 10 major research areas. We have machine learning, deep learning, natural language processing, computer vision, robotics, expert systems, knowledge representation and reasoning, planning and decision-making, speech recognition, and reinforcement learning. To architect modern intelligent systems, you must understand what each individual node does on its own and how to wire them together to solve complex problems. Let's start with the foundation of most modern AI applications, machine learning. Instead of relying on explicit rules programmed by a human for every task, machine learning algorithms identify hidden patterns within data to make decisions. The model learns from either labeled data, known as supervised learning, or it discovers hidden patterns in unlabeled data, which is unsupervised learning. Deep learning is a specialized branch sitting inside machine learning. It uses artificial neural networks with multiple hidden layers to learn hierarchical features automatically. Because of this structural complexity, it requires large datasets and powerful GPUs, producing state-of-the-art performance in tasks like image recognition. Reinforcement learning operates on a completely different learning cycle. Here, an intelligent agent learns through trial and error by interacting directly with an environment. It takes an action, receives a reward or penalty, and uses that continuous feedback to maximize its long-term rewards over time. This photograph shows the AI system AlphaGo competing against a human champion. To navigate a highly complex game environment like this, the system relied heavily on reinforcement learning, improving its strategy entirely through continuous interaction and experience. Moving from learning models to how a machine perceives the world, we have to distinguish between speech recognition and natural language processing. Speech recognition is the mechanical step of converting spoken language, an acoustic waveform, into text. NLP is the linguistic discipline that allows the computer to actually interpret, summarize, or generate human language from that resulting text. You see this distinction in consumer hardware, like this smart speaker, which relies on speech recognition software to convert your voice commands into a text format the system can use. The raw data format dictates the tool. You use speech recognition to translate raw acoustic signals into text, and then you apply natural language processing to extract semantic meaning from that text. This interface shows computer vision in action. By imitating the human visual system, this discipline enables computers to analyze live images and video feeds for tasks ranging from object detection and image segmentation to real-time face recognition. When an AI system needs to interact with the physical world, we use robotics. This field combines artificial intelligence with mechanical engineering and control systems to build machines capable of autonomous movement, object manipulation, and navigation, like these robotic arms on an industrial factory floor. Behind physical actions and perception lies logical reasoning. We group 3 specific areas here: knowledge representation and reasoning, which stores structured knowledge like semantic networks; expert systems, which use an inference engine to imitate human domain experts; and planning, which determines the exact sequence of actions required to achieve a specific goal. This logic is applied heavily in domains like medical diagnosis. Clinical decision support systems store vast amounts of medical knowledge and use expert system inference engines to replicate the reasoning process of human doctors, evaluating scans like these MRIs. Learning models and perception algorithms allow a system to interpret its environment, but it is the structured reasoning and robotics capabilities that allow the AI to calculate logical decisions and safely execute physical actions. Let's apply this. Pause the video for a moment and think through this challenge. If you were engineering a self-driving campus shuttle, which of the 10 AI areas we just discussed would you need to include in your system architecture? This table maps out the integrated architecture required to make that shuttle operate safely. You would use computer vision to detect roads and pedestrians, machine learning to absorb driving patterns from historical data, planning to determine the optimal route, decision-making for safety actions, and robotics to physically control the steering and acceleration. All of those integrated systems run simultaneously, feeding off constant perceptual data inputs, like this sensor fusion display mapping out obstacle distances and positioning in real time. We see this same integrated approach in software applications. This chart illustrates how a system like ChatGPT operates. It relies on natural language processing to generate text, but it also requires deep learning to understand complex language representations, machine learning to train on large datasets, and reasoning to produce logical, context-aware responses. Modern software engineering avoids working in isolated silos. Complex applications emerge only when you architect these individual AI disciplines into one cohesive pipeline. To consolidate what we've covered, this matrix directly compares all 10 AI areas. You can see their primary focus mapped to core applications, serving as a study guide. These interconnected disciplines drive automation across industries, from healthcare to autonomous transportation. But deploying these systems involve real constraints. You will have to solve for high computational costs, massive data requirements, data biases, and security risks. Synthesizing these specialized functions into a single system with human-level flexibility is an unsolved hurdle known as artificial general intelligence, or AGI. This brings us back to our entire ecosystem. We have explored how learning, perception, reasoning, and physical action interconnect to form the technological foundation of modern AI. Thank you for joining this lecture from the UUM School of Computing. Mastering the distinct functions of these 10 areas is your first step toward building the safe, ethical, and complex digital ecosystems of tomorrow.